We have been discussing about the existence and the uniqueness of solutions of initial value problems. We have so far proved the Picard's existence and uniqueness theorem and also Cauchy-Peano existence theorem. These proofs were involved, and we used many notions from real analysis to prove the existence and uniqueness part. And if we make use of the functional analytic technique, especially the fixed point theory, then this existence and uniqueness of the solution of an initial value problem can be very easily established without much effort. In this respect, the Banach contraction principle can be applied to derive the existence and uniqueness of solution of an initial value problem, provided the function in the initial value problem is good in the sense if that satisfies Lipschitz condition. And also the Banach fixed point theorem will give us a way to compute the solution of the initial value problem. In the preliminaries, we have already seen the fixed point theorem, Banach contraction principle, and also a generalization of the Banach contraction principle. And let me just recall the Banach contraction principle. If X is a, say X is a normed linear space, and then the space is complete with respect to the norm, and we call this is a complete normed linear space. Let X be a complete normed linear space. A complete normed linear space is called a Banach space. And T is an operator from X to X such that T is an operator. This could be a nonlinear operator. So T is called a contraction if Tx minus Ty, the norm of Tx minus Ty is less than or equal to alpha times norm of x minus y for all xy in X and for some alpha strictly less than 1. Of course, this has to be a no negative number. If a T is a contraction, example if fx is a function defined by half x, it is a linear function. So it follows easily that f is a contraction. F is a contraction. If is Lipschitz continuous and the Lipschitz constant is less than 1, then is called a contraction. If is Lipschitz with the Lipschitz constant half, so here alpha is equal to half. Another nonlinear example is say fx is 1/4 sin x, and we have already seen that sine function is Lipschitz continuous. So therefore 1/sin x is also Lipschitz continuous with Lipschitz constant 1/4. So this implies that f is a contraction on R. R is a complete normed linear space, a Banach space. Now the Banach fixed point theorem says Banach's fixed point theorem says or known as Banach, also known as Banach contraction principle. Banach contraction principle. If T from a Banach space x to x is a contraction, then T has a unique fixed point, say x star. That means T of x star is same as x star. The point x star is a fixed point. Further, if T is a contraction, then T gives a unique fixed point. At the same time, it gives a computational algorithm to find the fixed point. Further, the sequence xn defined by xn plus 1 is equal to, or xn is equal to T of xn minus 1. So, x0 arbitrary, so n is 1, 2, 3, etc. The sequence xn defined by xn is equal to Txn converges to the unique fixed point, T star of T. So, this is a computational algorithm. We will see later that this is nothing but the Picard's iterants which we defined earlier. So, just example of a fixed point. See, if I have an function f x is equal to x square. So, obviously x is equal to 0, that f of x is equal to 0 square, that is 0, x is equal to 0 and x is equal to 1 are fixed point. Of f x is equal to x square. See, geometrically, if you look into the graph x square, and fixed point is, in a one dimensional case, the point of intersection of the function y is equal to x and the given function. So, there are two fixed points, so 0 and 1. So, this gives you the fixed point, two fixed points are there, and f x is equal to x, all points are fixed points. F x is equal to x cube, so you can find out the fixed point. They are the point of intersection of the graph of the curve with the diagonal line. Okay, now let us come back to the initial value problem. So, the initial value problem. So, we have the initial value problem dy by dx is equal to f of xy with initial condition y at x0 is equal to y0. And now we state and prove the existence and uniqueness theorem for this initial value problem, and the proof of the theorem will be based on Banach contraction principle. So, let me state the theorem. Theorem is so let f x y be a continuous function defined on a domain D of R2 . So, let f be Lipschitz continuous on D, Lipschitz continuous on with respect to y, Lipschitz continuous with respect to y on D. Then of course, other conditions like x0 y0 is an interior point of D. Then there exists a unique solution to the initial value problem. So, this is our initial value problem. On an interval x minus x0 less than or equal to h, where h is minimum of a b by m and m is maximum of f x y x y is in some rectangle R which is inside D. So, R is a rectangle defined as earlier x y such that x is x minus x0 is less than or equal to a, y minus y0 is less than or equal to b for some a and b such that this R is inside the domain D. So, the theorem is if f is continuous is a continuous function on D and if is Lipschitz continuous with respect to y on D, then there exists a unique solution to the initial value problem on an interval x minus x0 is less than or equal to h, where h is defined by this, where a and b are parameters of a rectangle which is inside the domain, and let us alpha be the Lipschitz constant of f. Of f with respect to y. So, further we have the unique solution can be computed from the successive approximation y of n minus 1 x is equal to y0 plus integral x0 to x f of t yn of t dt n is equal to 0, 1, 2, etc. So, this iterative scheme, if you recall, this is the Picard's, known as a Picard's iterants. So, same sequence of functions which we constructed in Picard's iteration. Okay, and y0 function is just y0. You can start from any arbitrary y0 n is y0. Okay, the proof of this theorem we will state by using Banach contraction principle, and also we note that in the Banach contraction principle, if T is a contraction, then T has a unique fixed point. If Tn is a contraction, if Tn is a contraction, okay, if T is an operator from a Banach space X to another Banach space X, if Tn is a contraction for some n greater than or equal to 1, then also then T has a unique fixed point. So, this is known as a generalized Banach contraction principle. Generalized Banach contraction principle. So, we will be using this generalized Banach contraction principle to establish the proof of existence and uniqueness of solution of the initial value problem. So, let us come to the proof. Proof So, by the basic lemma, so from the basic lemma we stated and proved earlier, basic lemma, the solvability of the initial value problem follows if the following integral equation is solvable. The integral equation from the basic lemma ys is equal to y0 plus integral x0 to x f of t y of t dt. So, we have proved that if you want to solve the initial value problem, it is enough to solve this integral equation. This is known as a mild solution of the initial value problem. So, therefore, we are looking for a solution of this integral equation, and let us define an operator. So, let us define first a function. Let x be a function C a b, C set of all not a b. So, our interval is, we are looking for a solution from x0 to x0 to x1, for some x1 greater than x0, set of all continuous functions defined on the interval x0 x1. And it is easy to solve that, show that this X is a Banach space. So, if we define a norm, so define a norm for X in X, norm of X is supremum or maximum of x of t, where t varies between x0 x1. It is called the sup norm or max norm. So, x is a set of all continuous functions. So, supremum and maximum, they are the same in this interval x0 x1, closed and bounded interval. So, therefore, X is a norm linear space. X with this norm is a normed linear space, and also it is complete. Every Cauchy sequence in X with respect to this norm converges to a limit inside. So, therefore, it is a complete norm linear space. It is a complete norm linear space, that is a Banach space, is a Banach space with sup norm. Now, we define an operator. We define remember our integral equation is yx is equal to y0 plus integral x0 to x f of t y of t dt. Now, I define an operator define a mapping or an operator, call it T, from C x0 x1 to itself by T of y is a function at x is equal to y0 plus the right hand side of your equation, call it equation 1, right hand side of equation 1, y0 plus integral x0 to x f of t y of t dt. So, f is a nonlinear function, and so therefore, t is a nonlinear operator from the Banach space C to C. Now, if t has a fixed point, if t has a fixed point, that is, if you can find some y such that y is equal to t y, then y is equal to t y, y is equal to t y for some y, then that is nothing but your integral equation. So, therefore, the solvability of the integral equation 1 is equivalent to the existence of a fixed point for the operator t. So, therefore, my objective is to show that t has a fixed point. If t has a fixed point, that is there exists a y such that y is equal to there exists a y such that y is equal to ty, then the fixed point y is a solution to the integral equation. Integral equation 1. If t has two fixed points, then integral equation has two solutions. If t has a unique fixed point, then the integral equation has a unique fixed point. If the integral equation has a unique solution, then the initial value problem has a unique solution. So, there is an equivalence between the solution of the initial value problem and the integral equation. If t has a unique fixed point, then the integral equation 1 has a unique solution. So, we are going to show that this operator t has a unique fixed point, and we will show that Tn is a contraction for some n greater than or equal to 1. So, we will prove that Tn is a contraction for some sufficiently large n greater than 1. So, how do we go about it? So, let us define. So, by definition t of y of x, t of y of x is y 0 plus integral x 0 to x f of t y t dt. This is a definition of the operator t. So, let us find what is t y 1 of x minus t y 2 of x. If y 1 and y 2 are two functions in the Banach space, okay. So, if let y 1 and y 2 are 2 points C x 0 x 1, two continuous functions, then we take this difference and the absolute value. This is absolute value of integral x 0 to x, y 0 and y 0 will get cancelled, and what we have is f of t y 1 t minus f of t y 2 t dt, and this is less than or equal to, and also by using the fact that f is Lipschitz continuous with respect to the second argument y. So, therefore, this is less than or equal to alpha times integral x 0 to x y 1 t minus y 2 t dt. So, this is one relation we will be call it equation number 2. Now, this is also greater than or equal to alpha times integral x0 to x. If I take the max of or soup over t in the interval x0 x1 y1 t minus y2 of t, I can take this is greater than or equal to dt, and this quantity is our norm of y1 minus y2. So, this is norm of soup norm y1 minus y2. So, therefore, for this is less than or equal to alpha times integral x0 to x norm of y1 minus y2 dt, which is equal to, if you integrate it, now y1 norm of y1 minus y2 is a constant. So, alpha times x minus x0 into norm of y1 minus y2. All right. So, if I take now t square, so my aim is to find an n such that Tn is a contraction. Now, if this constant alpha into x minus x0, if I can bound this by a number which is less than 1, then t is a contraction, but this I cannot have unless I put some restriction on the Lipschitz constant alpha. So, but I do not have any restriction on the Lipschitz constant alpha. So, what I do is I take a composition, I take a t square. So, t square y1, so t square y1 of x minus t square y2 of x, which is nothing but the composition of t with the t 2 times. So, this is t of t y1 of x minus t of t y2 of x. So, this is less than or equal to, if I use 2, this is less than or equal to alpha times integral x0 to x t of y1 of t minus t of y2 of t dt. Now, using the inequality, call it this one. So, 3, if I use 3, t y1 minus t y2 more, okay, absolute value of t y1 minus t y2, okay, from this equation number 3, I get this is less than or equal to alpha square times integral x0 to x, okay, so it call it t minus x0. So, x minus x0 becomes t minus x0 times norm of y1 minus y2 dt. Okay, this I can integrate to get alpha square by integral of t minus x0 with respect to t is a t minus x0 square by 2. So, alpha square by 2. So, t minus, that is evaluating from x0 to x. So, t x0 minus x0 is 0. So, therefore, this is x minus x0 square into norm of y1 minus y2. So, this is times norm of y1 minus y2. Supra. So, therefore, what is the conclusion? If I take the supremum of this quantity over x varying on the interval x0 x1, then that becomes a norm. So, norm of t square y1 minus t square y2 is less than or equal to, if I take maximum over there, I get alpha square into x1 minus x1 is the maximum, x1 minus x0 square by 2 factorial into y1 minus y2. So, I can continue this procedure. So, if I continue this procedure to take one more times t composition. So, tq y1 minus tq y2 just by integrating, that integration is a process which is making the right hand side a good number. So, tq y1 minus tq y2, which you can show that this is less than or equal to alpha cube by x1 alpha cube into x1 minus x0 cube by 3 factorial times y1 minus y2. So, if you continue like this, Tn y1 minus Tn y2. So, Tn y1 minus Tn y2 can show that this is less than or equal to alpha to the power n x1 minus x0 to the power n by n factorial into y1 minus y2. So, what does it say? If my n is sufficiently large and x1 minus x0 is a finite quantity and alpha is a Lipschitz constant and the denominator I have n factorial, this can be made. So, can be made less than 1, strictly less than 1 if n is sufficiently large. So, therefore, without any additional conditions on the Lipschitz constant of f, I can show that, or we have seen that Tn is a contraction. So, this implies that Tn is a contraction and hence Tn is a contraction for n large, for n large, and hence T has a unique fixed point by the generalized Banach contraction principle. So, therefore, this Banach contraction principle, this proof gives us both existence and uniqueness. So, Tn is a contraction, means T has a unique fixed point. The unique fixed point happens to be the unique solution of the integral equation that amounts to be the unique solution of the initial value problem. And further, the computation of the fixed point, as we have seen, x n plus 1 is equal to t of x n. So, starting from any arbitrary x 0, that gives us the or a sequence x n, that converges to the unique solution of the initial value problem, or converges to the unique fixed point. So, in our context, so y of n plus 1 is equal to t of y n and y 0 arbitrary. By definition of t, so y n plus 1 is y n plus 1 is a function of x is equal to y 0 plus integral x 0 to x f of t y n t dt, and you choose the initial function y 0 t y 0 x as your y 0. Y 0 x is your initial condition y 0. In fact, this iterative scheme, if we compare with the Picard's existence and uniqueness theorem, this is a Picard's iterative scheme. Let us see one example how the initial condition is, or how the solution is computed by using this Banach fixed point theorem is illustrated in the following example. So, example, let us take a very simple system, a linear dy by dx is equal to y, where y at 0 is 1, which we all know the solution. Okay, it's a linear equation. The solution y x is e to the power x, we know the solution a priori. Okay, here what is f? F of x y is y, which is Lipschitz, and if it is continuous with respect to both the variables and also it is Lipschitz with respect to the second argument, and it satisfies all the properties. So, let us define the iterates. So, y 0 x is a initial function, initial condition 1, and y n plus 1 x is equal to y 0 plus integral 0 to x, here f n is y n t dt. Okay, so therefore, what is y1 x is equal to y 0 is 1 plus integral 0 to x y 0 t dt, and y 0 is your 1. So, this is equal to 1 plus integral 0 to x 1 dt. So, which is equal to 1 plus x, and y 2 x is again 1 plus integral 0 to x is y 1 t dt, which is 1 plus integral 0 to x, y 1 is 1 plus x. So, this is 1 plus t dt. So, which is equal to we get 1 plus x square by 2. And similarly, if you find y 3 x, it is not difficult to show that y 3 x is 1 plus x square by 2 plus x cube by 6 and so on, and you can see yn x is summation x to the power m n by n factorial. Yn is x to the power m by m factorial, where m goes from 0 to m. So, this as n goes to infinity, this goes to e to the power x as we expected. So, therefore, the computation of the fixed point by using the Banach contraction principle, that amounts to be the Picard's. We see that this is nothing but the Picard's iteration, and by using that one can compute iteratively the solution of a initial value problem, provided if those good conditions of Lipschitz continuity etc. are already satisfied in the equation. Okay, so this portion completes the existence and uniqueness of solution of initial value problem. So, we posed 3 problems initially: the Hadamard well-posedness problem. A model is well posed if a solution exists, the existence problem, and the solution is unique, the uniqueness problem, and the solution is stable. Stable in the sense if the solution changes continuously with respect to the initial condition, then the solution is stable. All these 3 properties of 3 conditions of Hadamard, the one is left out is the stability, the third condition. We now look into the stability aspect of the solution of the initial value problem. So, stability of solution with respect to initial condition. Okay, consider the initial value problem. Consider the initial value problem. dy by dx is equal to f of x y with initial condition y at x0 is y0. And if I change y0 to say y0 tilde, if with y0 I have a solution say yx, and what will be the corresponding solution of y0 tilde? What is the relationship between? If y0 is changed to y0 tilde, and what happens to the solution y, and what will be the relationship or how much close, if y0 and y0 tilde are very close, how close y and y tilde, the corresponding solutions? That is our question. In other words, it comes practically in many applications, because in many experimental data, the initial data we take from the instrument, from a device. While taking the reading from the instrument, either the instrument may not be that very accurate, or the person who is taking the observation is not very keenly taking. There may be a possibility of a little bit error in the initial data y0. If a slight error in the y0 makes a slight error, a corresponding small error in the solution, then the solution is reliable. Then we say the solution is stable if a small change in the initial data results in a small change in the solution, then the solution is stable. A small change in very small change in the initial data results in a drastic difference in the solution, then that solution is not reliable, it is not believable. So, therefore, we want to make sure that the solution is stable in this sense. So, mathematically it is nothing but the continuity of the solution with respect to the initial data. So, stability is the continuity of solution with respect to initial data y0. Again, if our function f is nice, if f is continuous with respect to x and y, and f is Lipschitz continuous with respect to y, then the stability is also guaranteed. So, I state and prove that as a theorem, if the differential equation is in the differential equation f, if f is continuous with respect to x and Lipschitz continuous with respect to y, then the solution is continuous changing continuously with respect to the initial data, or the system is stable. So, I state and prove the theorem. So, theorem is suppose that f of x y is continuous on D a subset of R2 and Lipschitz continuous with respect to y on D, then the solution of the initial value problem dy by dx is equal to f of x y, y at x0 is y0 is stable, or solution changes continuously with respect to the initial data. So, the initial data y0. So, proof is straightforward by using Grunwald's inequality. Proof: let y0 and y0 tilde be two initial data points, and so since f is Lipschitz, it has a solution, it has a unique solution for every x0, every y0, since with y0 there exists a unique solution, and y0 tilde also there is a unique solution. So, because of the Lipschitz continuity. So, if we choose the two initial conditions y0 and y0 tilde, there are two unique solutions. Okay, let y x and y tilde x be the corresponding solutions of IVP. Okay. So, such solution exists and such solutions are unique. So, therefore, what we have is corresponding to y0 we have a solution yx is equal to y0 plus integral x0 to x f of t yt dt, and with the y0 tilde the solution is y tilde x is equal to y0 tilde plus integral x0 to x f of t y tilde t dt. So, there are two solutions. If I find the difference, say yx minus y tilde, and I take the absolute value which is less than or equal to taking the difference y0 minus y0 tilde plus integral x0 to x, and since f is Lipschitz continuous with respect to the second argument, one alpha comes out. So, this is yt minus y tilde t dt by Lipschitz continuity. F with respect to y. Now, using by Grunwald's inequality, okay, we can see left hand side and right hand side both you have yx minus y tilde. So, that can be bounded by another function on one side, that is yx minus y tilde x is less than or equal to y0 minus y0 tilde into exponential alpha times integral x0 to x dt, and this can be bounded. This is less than or equal to y0 minus y0 tilde e to the power alpha into x minus x0, and x minus x0 this can be bounded by h, or if we take x1. Okay. So, that is h less than or equal to y0 minus y0 tilde into e to the power alpha x1 minus x0. So, what does it say? It says that yx minus y tilde x is less than or equal to y0 minus y0 tilde e to the power alpha x1 minus x0, which is a finite quantity. And so, whenever y0, so for every small change in y0, the difference between y0 and y0 tilde is small, then the corresponding difference between yx and y tilde is also small. So, for every epsilon greater than 0, there exists a delta. The delta is given by epsilon by e to the power alpha x1 minus x0. If I choose this delta, then it follows that this y is continuous with respect to y0. So, now it is obvious that the solution is also continuous with the initial data. So, therefore, if a function, if the initial value problem, the function satisfies a Lipschitz type condition, then the solution is also stable with respect to the initial data. Okay, so, with this we finish the stability aspect of the solution. We have seen the existence, the uniqueness and stability. Okay.